Well, hey there, guys. We're back, and we just have a quick wrap up for notes, angular momentum day 2. So just a quick recap. Angular momentum is our rotational counterpart to linear momentum. All right, angular momentum, number 2. All right, so it's our counterpart to linear momentum is here, right? mv, my angular momentum, I omega, if I'm dealing with an object that's a regular geometric shape, or we say mvr if we're dealing with a point mass. That being said, again, remember that your point mass, you don't have to be rotating to begin with. It could just be moving in a straight line if this is your point mass. And then basically, based off of, let's say it's over here, let's figure that for any radius that you decide, say you decide, oh, let's consider we have this rotating object over here, you can now describe that particle as having an angular momentum. It doesn't seem to make a ton of sense at first, but when you consider the fact that we can't create or destroy momentum, and we have angular momentum, say, after a collision, you have to be able to describe it before a collision as well. So MVR is a great way to do that. All right, so the focus right now is going to be on calculus, our friend, our little friend calculus. All right, so this is the key relationship piece, these two pieces that we want to make sure that we get back to. All right, so let's consider. When we look at linear momentum, if we're dealing with the calculus relationship, what we're looking at is, well, we have force and time. That's our definition of impulse, right? And it's when we have some sort of squiggly sort of thing and our area under the curve. Our area under the curve is going to be the change in that momentum. So the relationship that we're looking at is we take the area under the curve with respect to time, and that would give us our linear momentum. All right. Also, conversely then, if we took the derivative of the momentum function with respect to time, whoops, t, sort of looks like a t, right? We would get the force. Let's look at that from the calculus perspective. Okay, same idea, except again, we have to start taking things and using the rotational counterpart. So instead of force, we say torque. Time doesn't have one, right? But we're looking at whatever that function is. And again, we want to take the area under the curve. And that area under the curve is going to be equal to the change in angular momentum. So that relationship we're looking for, if we want the area under the curve, is we're going to take the integral of torque with respect to time. That's going to be the change in angular momentum. Conversely, if we take the derivative of the angular momentum with respect to time, we should get the torque. It doesn't come up often, but it's a good one to know. Last but not least, let's go back to our definition of collisions. Let's give me a new page here, buddy. No. Oh, I guess I didn't put one in. So, well, when you're done, if you need to pause so you can write, go ahead and pause so you can write, because I got to make some space. Let's remember our definitions of collisions. All right, elastic versus inelastic. This basic idea also applies to rotation as well. If we're dealing with an elastic collision, this means that we have to conserve the angular momentum as well as the kinetic energy, which, as we know, in reality is a little tough to do. Right, in elastic collisions, we still conserve the angular momentum, but not the kinetic energy. All right, so these are the basic big strokes. We obviously need to have a lot of practice, but we will get to that in a bit. I want you to give 87M3 about 15 minutes, give it a try, and I will go over that answer in the next recording.